This has been a joint effort with several different groups. We went out to talk to professional penetration testers at Leviathan Security, and you will see some of their input in here, because the kinds of things that we substantiate with analysis of protocol syntax, they just know, and they aim for them in their penetration tests. And then we have help from the Technical University of Hamburg, their recently created cyber physical group, where Sven Holberg helps us with the DNPC testing and implementation. And of course, Meredith Patterson has been our co-author on the language theoretic analysis of protocols since the beginning. So a broad group, and we're going to talk about this problem that's been plaguing protocol implementations. We found it much more acute in ICS protocols, even though some of the examples that I will be giving are from garden variety internet protocols as well, just that ICS protocols have not been pounded on sufficient. And what I want you to keep in mind is that this byline, the data format is code's destiny. Our contention is that you lose the security game at the point when you've designed your data, not even when you start coding, but at the point when your data format is just too complex for the programmers to implement correctly or unambiguously. So we started with this with a very practical goal in mind. Namely, you go through the airport and they tell you, remember 311, right? Remember 2 plus 2. A typical pen test, a typical code audit is 2 plus 2, 2 persons, 2 weeks. And this compares very unfavorably to attackers who have infinite time to just find one vulnerability to attack you. Now, as penetration testers well know, coming up with the proof of exploitability, even after you find a weakness, can take weeks of concerted effort. The 2 plus 2 just totally precludes it. So what they do and what they want to do is confirm departures from safe design practices. And basically pretty much every big programming shop, including, say, Google and Microsoft, have gone that way. They do not want to see internally proof of exploitability. They want to see a departure from safe design. So what we want to be able to say is, look, this protocol is trouble. This parser is trouble. This data format is trouble. This protocol spec is trouble. And we want to be able to say it in a way that a pen tester and auditor finds a finding. A finding is something that can hold the release hostage. And it is being enshrined in the common weakness enumeration as opposed to common vulnerability enumeration. Vulnerability presumes that there is an exploitatory demonstration of exploitability. A CWE is a thing like a poor design code, poor code design, poor data design. So we want those CWEs. We don't have them yet. But the bad feeling is not a finding. So if we could do this every time we found a protocol that exhibited one of those weaknesses, and would be in a much better shape. So what we want to do in our program was to give this bad feeling a theory and enhance some existing weakness enumeration, such as indicator of poor code quality. We would also want to apply it to data. And essentially, we want to give auditors a weapon against things that will make things go wrong in parser design, protocol design, or format design. And eventually, we want to get them into the CWEs and give them their official numbers. And notice that CWE already has things like improper input validation, but those are just really non-specific. If you look at them, you will see that it's improper input validation, improper neutralization of input, improper neutralization of special elements in input. That doesn't tell you anything about how to design the protocol. You know, why are those elements so special? Why are they trouble day in, day out? And secondly, it's kind of strange. How do you neutralize them? What does it mean to neutralize your input, right? So there is some intuition here, but it must be unpacked. The problem with those descriptions is that they describe mechanisms, and they are the wrong level of abstraction. So they don't let you find out anything about the cause of why things are wrong. They are consequences of bad design, symptoms, not a descriptional one. So it's not something that you can recognize as a root cause up the line. So what is input validation, and what is it good at? So we take the computational complexity view of this, and everyone is telling you validate inputs, validate inputs. That by itself is not a very helpful bit of advice, as we've been finding out over and over. This implication that valid is safe is just not there. You can download valid C, you can compile it and run it, and you won't be safe at all. So safe means predictability, not causing unexpected operation. This has something to do with validity, but the connection is not immediate. And this is where protocol design and protocol implementations go wrong. So this concept of validity must mean that once you've validated it, once you've verified it, what happens next is predictable. Otherwise, this concept is useless. Now, if you take a general computing language, general purpose computation language, you can't predict what it does, even though a program may be valid. This is your halting problem. This is your Rice's theorem. You cannot make a judgment about behavior based on this validity. CW's neutralization kind of sort of has this intuition. It implies that input is active. It's a program. It must be neutralized. It must be rendered inert to be safe. And so we have to look at the input from this point of view, that it is something that causes computation. Your program is a reactive system. And you must make it easy to judge its behavior. So the next almost trivial consequence of this is that you must make the judgment as simple as possible. So you have the checking code. This checking code is your only defense. It should not be capable of running away. It should be capable of being verified itself. And you have this issue with non-trivial properties of Turing-complete programs that can't, in fact, be automatically verified. But the programs for simpler automata can be. That's why your protocol should admit simple automata for its concept of validity. Because this is where your only hope of avoiding trouble lies. And so you have this relationship between the data format and the parser structure. One reflects the other. Quoting Greg Morissette, everything is an interpreter. So we can say everything is a parser. Quoting, well, myself actually, but stolen blatantly from Asimov, every sufficiently complex input processor is indistinguishable from a VM running inputs as byte code. But for this talk, it's data format is code's destiny. And so if you look at this from the CR-HOR style verification, you have this chain of preconditions and postconditions, and every postcondition implies a precondition. The problem with this chain, it is brittle. If you break any one of those assumptions, then what this code does and what you have proven are completely different things. So you must formulate and verify assumptions. Your most typical case is of a programmer making an assumption about input. That assumption is not validated, and the code that was just fine becomes a part of the exploit machine, exploit engine. So, of course, all of our systems are multi-layered, and there is this overarching weakness principle that is a failure to communicate assumptions to interacting modules. So somewhere down the chain, this chain breaks. So compared to all other kinds of engineers, we have this issue that what we do is not stable with respect to our best tool, right? A mechanical engineer works with the concept of stability, and there is a concept of stability. We, on the other hand, with those stacks of layers and chains of assumptions, do not have stability. So, what is your proof more like? And so you come at this recognizer pattern that we have been promoting that basically says that you must specify your assumptions in a formal way, and not just in a formal way, but its properties must be checkable with the simplest possible automaton. This is your recognizer. This is your best shield against unpredictable behavior by the rest of your code. This is where the concept of input validity actually plays out and becomes a defensive tool. If the behavior of the rest of the program can be judged based on it, then it's good, it's useful. When it's not so useful in judging how the rest of the program will behave, then it isn't. And what you see in this picture is really just the first clause in the CR4 verification chain, just depicted in a better way. If you don't have your recognizer enforcing your post conditions and checking your pre-conditions, then you have no accessibility for the rest of the proof. That's really what this picture says. That's what we want to have. This is usually sort of what we get. Instead, we get the really weird anti-patterns, and I could not resist putting in this image in here, because this is really what you find in production. This is where our auditors come in and basically help us enumerate those. And so I'm going to talk about these 7 different flaws, not with the same amount of detail. And I'm going to use DNP3 SA, a proposal for authenticated DNP3 for some of the examples. And I'm going to use classic stuff like Heartbleed for others. So the first anti-pattern is what we call the shotgun parser. Just fire a cloud of checks at the input. And those who've heard me speak before certainly remember the term, I hope. The way it violates the pattern of input validation is that there is no clear boundary after the input can be considered checked and safe. And you really want your auditor to be able to hold your code hostage over this. Heartbleed will remain for years a perfect example, right? So you've got nested records and links describing the same package in every every such record. So the question is, which of the 2 links, the containing one or the contained one, do you trust? And of course, what the OpenSSL trusted was the inner links, didn't check that it was the same as the outer links, should have been less, of course, because you have to also accommodate the request type. And instead of 1 byte of data, you echoed back as many as a 2-byte length value would allow. And these are the pieces of code that are here. This is the vulnerability. But if you look at this, you ask yourself, does it really look like the parser? This pointer arithmetic thing on top is not really checking any condition, does it? And if it were, what sort of a condition would it be checking? How is the data structure, the expectation of the data structure reflected in this code? And the answer is it isn't really. So this is an anti-pattern. This is code that's extremely hard to audit, and you don't have any clear idea what is being checked, what has been checked. How will you construct your chain of predicates that will eventually prove that this program is correct? And you can't. And now let's look at the fix, right? So the bad code is up top. The good code, the fix, is the middle hunk of the diff. And again, you look at this code and you have absolutely no idea what it does. What is it checking? Why is it checking? What are all of those integers? So this was a shotgun parser. This remains a shotgun parser. And here's another thing, right? You're reaching for the data before it's been checked, before it's been baked. There is no boundary at which point you consider it safe. So don't do this. Premature processing of unvalidated input is really what we see here. And if you think that this is limited only to OpenSSL, you'd be very wrong. Because here is, SSL is arguably an old process, an old protocol, and a Baroque one. And what do we even need that heartbeat message functionality for? But here is DNP3, a newcomer. This is the long-awaited part where DNP3 objects are cryptographically signed, authenticated. And in fact, out of that's 21 of 33 function codes that can be authenticated. And you can defer the parsing of those payloads until authentication. This is a great feature because you don't want to parse what might be hostile. If you can avoid parsing tempered data, you should definitely do so. In fact, this is what Moxie Marlinspike called the cryptographic doom principle. If you, for encryption, if you decrypt before you authenticate, something wrong will happen. You will probably have an oracle for your encryption because you're essentially giving the adversary the ability to tamper with the data and to engage with your cryptographic internals. So have we solved the problem then? And not by far. Again, formats rear their ugly head again. Syntax rears its ugly head again. So first is that this format requires this protocol allows signed and unsigned elements to be mixed. And DNP3 is complex enough. You cannot easily skip over an unauthenticated element that you don't trust to get to the signed element that you do trust. In fact, this is a chain on a sum of length fields, and so you are still forced to parse unauthenticated data. To make things even more hairy, the state is affected by both signed and unsigned messages. So even though you can now hold off parsing until authentication, for some things, your state will be affected by those things that you cannot authenticate. So what you're ending up with is more complexity, not less. And even worse, you are creating multiple syntax ambiguities. So remember the Heartbleed example where you have two sources of truth, two lengths, and you've created a burden on your programmer to check that all of them correspond. In fact, in OpenSSL, you can have triples of lengths that you should check, and even quadruples for some messages if you construct them. Here, you have the same thing. So you can have a session key object, and there is this MAC authentication value. And how long is this value? How do you find it? Well, by the standard, its length is the remainder of the length field framing the entire object. So you start parsing into the object. You get a series of data objects, and then your authentication material is just what remains. So can you validate this element on its own? This element is most critical to your security, but instead, the description of it depends on the previous series of objects. So you're setting yourself up for an error. If you look at this from the syntax complexity point of view, you've just kicked the ball way out of the context-free grammar, or even weakly context-free, where your TLV can be handled more or less safely. So you're doing worse than OpenSSL that uses TLV, not better. And that's not the end of it. In fact, you have other data structures where you have several variable length fields, and the length of the challenge is encoded explicitly in one and implicitly in the other. And so as you read the proposal, it's like, oh, well, if one is not there, then you just take the other thing and make that the ground truth. Now, again, imagine the complexity that you have just created in the checking code, that nugget that has to handle the alternative, extracting either the implicit specification or the explicit and deciding what to do with them. It is not a happy place. So you've just, again, added an unnecessary context sensitivity to your specification. You just added a potential source of programmer confusion, and you just mandated by this data design a hunk of code where the programmer may easily make a mistake. And again, it might seem trivial until you look at it from the language theoretic point of view. How much complexity did you just add to the automaton that should be accepting this? Well, you pay for every bit. So that leads to another consideration. Not only should you check your validity in a non-shotgun manner with a clear boundary, with a clear specification, but if you make your syntax too hard, your judgment of what it would cause the rest of the program to do will be impeded. So make the judgment as simple as possible. Prefer the simpler checking clauses that must be applied. And of course, the computational power of the recognizer rises with the language syntax complexity. This is the Chomsky hierarchy that I spoke of many, many times before. And the theoretical statement here is, if you're in the Turing completeness territory, if you're looking for non-trivial properties, don't even try. But this goes all the way down to the make the syntax as simple as possible. Make the automaton validating it as simple as possible. Regular or context-free. That is what makes the concept of valid useful for security. This is the useful validity. Turing complete validity is not. Of course, a certain bank, well, the blockchain bank, the DAO, found out that yes, if you allow your input to contain Turing complete programs, then you will have a problem. And so this is the piece of code that got away with their entire balance. This is the Ethereum smart contract language, which allows recursion. It's underlined in here. And it locks the environment in which it's running. It's a virtual machine, so, you know, we should be safe, right? It's a virtual machine. It's a sandbox. No, because the concept of safety is only comes from being able to predict the behavior of your system on the code. So they set themselves up to distinguish between benign code and malicious code, and they failed. So this piece of code took a little bit off of their balance, then called itself, took another little bit, took another little bit, took another little bit. They ended up with having to do a hard split. That is to say, basically, essentially, declaring that these transactions and others since then did not happen. They set themselves up. They set themselves up for it, and they would earn. But again, you ask yourself, but surely we're doing better in ICS protocols. Surely something like DNP3, the core DNP3, does not contain executable code. That is correct, but syntactic complexity starts biting way before it gets at Turing complete. So these are several examples from the talk called Project Robust Master Serial Killer. It's already 3 years old. Adam Crane and Chris Sistron gave it at the S4 conference. And they had a number of devastating bugs in DNP3 that crashed the master controllers. So that talk, among other things, put to rest the argument that, yeah, you know, if you compromise a substation, nothing bad will happen. It's the master controllers that we care about. So yes, you can take down master controllers pretty easily by talking dirty DNP3 to them. And we're going to go through several examples of this where, again, you will see that complexity, unnecessary complexity that basically made the language not regular, bit and bit hard. So what you're looking at is the standard DNP3 header. So you see the type of the packet, unsolicited response. Okay, that's fine. Group and variation. And then you see, again, just a 2-byte field. And then you see the syntax element that is just going to be trouble over and over. You see, instead of describing the contents of the pattern, of the packet, instead of describing the length of the packet even, it has the starting index of this width and the ending index of this width into the object stream that is being transferred over DNP3. And so this packet by itself is already deadly because, look, what do you do if you're told that you need your object start at 0 and end at FFFFFFFF? Your master controller crashes. You probably did not expect it. It goes into an integer overflow, possibly, or maybe into an infinite loop for some other implementations. There is no data, but so that's the whole of what you sent. But this start index and end index is just syntactic poison. Here's another example. Same kind of a packet. This time it's a different group and variation. It's a different type of a message. And now the length field of this start and end index is just 1, so there are 2 bytes. And again, you use the maximum value for the second one, so probably not an integer overflow, still an infinite loop waiting for the missing data. Like, why? Why? I mean, this is probably the easiest thing to check if you're aware of it, but if you're not, then if your validator is not, then you just created yourself a huge trouble. And, you know, this is what is crashing real controllers, real master controllers. Just the very question of how much data is there. So here is a node 100 talking to a node 100. This is the unconfirmed user data packet. 1 byte payload is promised. None is delivered. So you see the CRC starting right where that 1 byte of payload should be. And that also causes a crash. So here is your length field that is separated from the payload field. So again, you have a case of context sensitivity. Again, certified crashes on the majority of implementations. It's the little things in syntax that kill you. Because, well, humans make mistakes. You know, the more code they need to write, the more mistakes they will make. Here's another example. This is not even malformed. You use this start and stop syntax, which is, you know, okay, so you've got one object, and the only problem here is that these objects are unexpected. So instead of the actual objects, you get the random sequences of bytes. This works. This crashes things. So again, your grammar should have specified what is allowed there. Instead, it's just objects with some implicit restrictions. Too bad. And that's another one of those max range start and stop indexes, which are just syntactic poison. So it's the simple things that break your grammar and cause you trouble. The third pattern is also related to this, but focuses more on what do you do when you have to serialize data. That module that receives it, what is its task? So non-minimalistic input handling. Essentially, the proper pattern there is that computational power belongs nowhere near input. Reflection, evaluation, all of those pieces, they should not be a part of the same code module that touches input. You should do nothing more than consume input, validate it, and deserialize it, and make sure that these are properly typed objects, well-typed objects. Any extra computational power is just privilege given for free to attacker. We have been seeing this in Java protocols, and as everything in life uses Oracle, especially auditing in colleges for reimbursement reports and things like that. But I digress. So do EDS protocols. Deserialization has been the plague of that area, of that domain. So this example is the more standard one. Here is a protocol that was created by Elasticsearch, and they allowed the user to send in scripts to drive their queries, groovy scripts. How groovy is that? You know, this is very cool. You're serving the customer This is popular in your data analysis operations. This is your big data, definitely relevant. Except they are accepting scripts. Scripts are executable. The effects of the script are very hard to judge. When you have a Java virtual machine, a JVM, that offers reflection and allows code to basically ring runs around itself, it is doubly hard to judge. And so what you're seeing here is this elastic shell, which is, of course, a joke. This is something that gives you the shell on the target. And you see the reference to Java runtime, accessed through reflection, and suddenly you're able to execute code of your choice. And there is a blacked out bit of hacker immaturity in there. This is the part where you send in your payload and you get it executed. So you've kept your evaluation a part of your input handling model, and it has been hijacked. Ruby on Rails has been a constant provider of this kind of thing. It started in 2012. It has not ended in 2016. So the latest 2016 CVE on this has this for a mitigation. Mitigate by casting the parameter to a string. Just reflect on this. What else is in there if you suppress it by casting it to a string? That's sort of an idea when why parse if we can eval? Because eval has a parser of its own, right? It will surely throw an error if the syntax is wrong. It's an anti-pattern. And as one of the researchers said, don't let your evaluation any close to user input, because it will get exploited. Shellshock, of course, I would be remiss if I didn't mention that. So here's your shell, which you make a part of your CGI, that is to say, the bit that receives the data off of the web and passes them on to a function called parse and execute. It's the execute part that is the problem. So the tremendous issue, penetrated all areas of infrastructure, because, of course, your generator, your transformer, is a web server. It has a CGI gateway on it, and when this is not going away. But this is fatally flawed. You should not be putting an executable engine anywhere near your input. It will get bypassed. You may believe that you have sanitized certain bad constructs, but this is the most powerful anti-pattern of all, because the validity of input is not the property of containing dirty bits. In fact, the expression that you sanitize your data is hugely misleading. You can't. It's not clean bits and dirty bits. It's the property of the entire message to be judged by an automaton to produce the post conditions that you can weave into your chain of eventual correctness proof. Parser differentials, I spoke about them before, so I'm going to be brief here. This is a big problem for any protocol that has context-sensitive syntactic elements. If you have two parsers and they must agree on what's in the message, then you're setting yourself up for an undecidable problem if these two parsers are, if these two recognizers are more powerful than deterministic context-free Undecidability starts as non-deterministic context-free, which is, mostly considered to be not that complex at all. And yet, you've just created yourself a problem where you can't verify the property of the code that your security depends on, equivalent interpretation. ASN1, X509 had this problem. You could not, you could have the CA and the client disagree on what was in the message. Android packaging scheme had that problem. You did not, you could make the Java package verifier disagree with the installer on what was in the packet, rendering signing of packages useless. Vehicle-to-vehicle standards that are coming up are based on ASN1. When cars disagree about messages they extend, I say good luck. So this is a very real problem, and it is a real problem for EDS protocols as well, because ASN1 is quite popular. So we really don't know what to do except transition to more strict encodings, certainly not BR, DR when possible, and subsetting of the language as much as possible. But it is, in fact, an anti-pattern. If you have to prove your two, that your parsers are equivalent and you have non-context free elements in your syntax, you're setting yourself for trouble right there. You're losing the security game right there. Incomplete specification is a variant of that. X509 had that in a number of occasions. SSL has this in a number of vulnerabilities. If more than one modular programmer is involved, when you can't answer unambiguously what is a valid input and what is the input that must be rejected, then how are you going to get that equivalence of parsers? Think back to the DNP3 examples that we just went through. Is the data there? Is the packet correct if it has indexes into the data stream but no data? Well, certainly some programmers thought that this was fine, recover somehow. But what you're doing there when you make an incomplete specification is that you're actually breaking that chain of assumptions. You're just not allowing it to exist. You've just eliminated the possibility of verifying or testing the correctness of your program. Overloaded fields are a very, very fun anti-pattern. When you have magic values that mean different things based on context, then the question is, what type system captures them? What language grammar includes them? You think that you're saving a field, but in fact you're creating yourself a huge headache. So NTP, which is a critical infrastructure protocol, we need to synchronize our clocks, right? And this protocol has had a cryptographic verification added to it. And it was just overloaded. You could have a value of 0 in that key field overloaded to mean, well, yeah, authentication is not required, skip this, which was mistaken by others to be this 0 key. You will find that you will find that particular angle on the NTP vulnerabilities and the anti-pattern in our LangSec workshop from last year, where we invited the person from the Cisco security who exposed this to present on it. And it's a very interesting exploration. But essentially what you did when you overloaded the field there, you blew up the hope of having any reasonable language grammar, any reasonable recognizer, because now you have to reach into the recognition process, have this special case, and so on. And finally, just about the worst one, which is luckily not so prevalent in EDS. We have not seen it in industrial control protocols, but we have seen it in browsers, and the Adobe Acrobat is probably the biggest offender, followed by Flash. At some point, Adobe had this idea that, oh, you know, if the document remains broken, well, we'll just apply those heuristic rewrites to it, which will fix it. And now we'll show it. So what you're actually doing is you are providing a piece of machinery for the exploit to co-opt. Rewriting systems are very powerful. Your lambda calculus, which is as powerful as it gets, is a rewriting system. So now you've broken any possibility of other people following the specification, because they now need to second guess what your rewriting system does. Microsoft made this mistake in Internet Explorer 8 when they applied regex rewriting rules to web pages that they rendered. And they actually made pages that were not vulnerable to cross-site scripting actually vulnerable after the rewrite. Amazing piece of cleverness, but you know, there you have it. You're giving away that machine. This is an anti-pattern. So along the same lines, Postel's robustness principle is trouble. And we were so proud for formulating this until we talked to Doug McElroy, who was, of course, there when Unix was being made and invented Unix pipes and wrote the code that's an echo and sort. And he said to us, oh, I always knew it was so. I always knew it was pure mischief. So do not try to fix invalid inputs. For the sake of the users, be definite. And there you have it. These are the 7 patterns that we identified that basically are the root cause of programmer error, and really blaming the programmers in those cases for not being careful when doing this unspecified input validation is yet another anti-pattern. These should be recognized weaknesses. We're working on documenting them to the standard, and they should be findings, and they should hold the release hostage. Now, to conclude, we have a workshop dedicated to this, language theoretic security workshop this year in San Jose on May 25th. And at the CRETC industry workshop, Prashant Nantaraman is going to give a talk on how we use the proper patterns and how we use the Parser construction tools for building better devices in IoT and the more hardened parsers for IoT protocols. Now, of course, it's funny that I should mention IoT on the very last slide, because, of course, if there is one area of engineering that is absolutely riddled with those anti-patterns, it's IoT. But there you have it, sort of the elephant in the room. And thank you for listening.
Right. Are there any questions? Questions online?
Are there any questions online? I don't know if they can hear you.
If there aren't any, then you can look at the paper that we presented on these anti-patterns at the IEEE SecDev, the first security development conference in the end of 2016 in Boston. It's a short summary, but it goes to more detail on a number of those bugs and why they were there.
You can find that paper on the CREDC website as well.